to move, right? Okay. Here, in this region here that I've sort of cut off here, right? Here they're increasing in kinetic energy. They're just going faster. How do you know they're going faster? What is one way we know that they're going faster in this region? What's increasing? The temperature is increasing. If the temperature doesn't increase, the molecules are not going faster, right? So they go faster and faster. We're gaining kinetic energy, right? A little graph reading. IB loves these. They love to give you these graph reading things. Where is the kinetic energy increasing? Well, it's increasing here. Is it increasing there? No, it's horizontal. It's something, the energy is going in, but it's not making them go faster. How about here? Are they going faster here? Yeah, faster here, faster here? No. Well, depending on whether you think that line's flat or not, but generally not, right? Not faster. How about faster? Are they going faster here? Yeah, there we go, right? So here, we're gaining kinetic energy, right? The molecules are going faster. We know that because it's rising, right? The temperature is going up like that, right? Here we're gaining kinetic energy. The molecules are going faster, right? And then here, in this region here, they're a liquid. They're moving faster and faster and faster. At some point, they cannot go any faster and stay connected with that, like the greased marble things, right? They're greased marbles. At some point, there's some little bond that keeps them close to each other, but not necessarily bound in a particular position, right? Whatever that little bond or energy or whatever it is, Van der Waals force, or I don't even know. I'm not really a chemist, but whatever it is, it's holding them together. In the case of greased marbles, it would be the force of the grease, right? Eventually, they're going to go so fast that that doesn't hold them together, and they fly off into the air, yes? Yes. That is boiling. It happens on the bottom of your pot, doesn't it? Yes, this water vapor forms. It's not air, it's water vapor forming at the bottom, and that's why it floats to the top and it boils, right? That's a rolling boil. So here, again, this is potential energy, right? And this is a phase change. We are breaking bonds, right? Some kind of a bond. Okay, so it doesn't go faster, it just breaks free. Yeah? Yeah, it takes a lot of energy. Look at that. Isn't that crazy? So energy is this way. It takes a ton of energy to do that. It's 7 times for water. In the case of water, it's 7 times the energy that it takes to melt the same amount of water. This one is like 3.33 times 10 to the 5th joules per kilogram, right? This one is 22.6 times 10 to the 5th joules per kilogram. We'll look at that in a sec here. So they cheated here. They added a little ellipse like that because they just didn't want to make the graph that big, right? It's like drawing a picture of the solar system or something like that, right? So what we have is, here we have ice, we have solid. Here we have solid and liquid, right? On this end, it's almost all solid, and on this end, it's almost all liquid. Here, it's half solid, half liquid. I never understood that, by the way. As a student, I thought that it sat there as a solid for the whole time, and then at one instant, boom, made this rapid transition into a liquid. Just instantaneously, boom. But it doesn't. Of course, ice cubes melt gradually, yes? Halfway through, you've got half ice, half water, yes? 3/4 of the way through, you have 3/4 water, 1/4 ice, yes? Yeah, I didn't understand that. I think I thought that until like college or something like that, right? Okay. How about here? It's all what? It's all liquid, right? Right? Here we've got what? Liquid, and gas. Here it's all. Imagine the container that's going to hold all of that water vapor, right? It's a big container. Big. There we go, right? So here's our phase change. The formula for this guy here, the formula for this guy is Q equals ml, right? Q is the heat added. Okay. And then this is the mass. So that's going to be joules, right? This is mass in kilograms. And then this thing here is called the latent heat. Where do you get the latent heat? Do you look it up in a table? Yeah, there's some table, right? KPA, whoa, look at us. Look how fast you're learning, right? You look those up in a table. Whoops. And this is in joules per kilogram. There's no degrees Celsius because It's not changing temperature, right? That should be your clue that it's not the one to use if the temperature changes, right? And then there are two latent heats. There are two latent heats. There is, this one is vaporization. Right, obviously we're turning it to a vapor. This one is called the latent heat of fusion. Not to do with nuclear fusion. Don't really know why we call it fusion. Fusing, I suppose when you fuse things, you melt them. I don't know. Anybody know why it's called fusion? Yeah. By the way, I never look at the name of them. You'll get two latent heats for a substance. Fusion is always the lower number, and vaporization is always the higher number. Why is it easier to melt something than to boil it away? Yeah, but why does it take 7 times? That's a good answer, but why does it take 7 times as much energy? What can you say? What is a liquid more close to being a solid, or is a gas more close to being a liquid? Much closer to being a solid. Water, liquid water has only a slightly different density than ice. Yes? Okay, but gaseous water has a very small density, yeah? It's compressible. It's a totally different thing, right? It's particles flying through space. Mostly a gas is nothing. A gas is mostly, by volume, nothing, really. Okay. Here are some latent heats. For water, as I promised, you would use, this latent heat here is 3.33 times 10 to the 5th joules to melt a kilogram. And this one is 22.6 times 10 to the 5th. So it's not quite 7 times as much, but there it is, right? If you're going to melt lead, well, there it would be, right? These are all joules per kilogram. Ammonia. Imagine vaporizing ammonia, right? Notice that these are all huge. Notice also that, and you don't need to write these down. Why am I writing vaporization with an S? Because when you take the IB test, it's all going to be British English, and so they're going to say aluminium, right? And they're going to say vaporization and all this stuff, right? Yeah. Yeah. I'd rather have you guys do whiteboards than write all those down. You can look them up in your book. Oh, there they are. Dewey Cheatham. Imagine melting, as in that trebuchet video. They melted lead. Were they wearing masks? I don't think I'd want to be around lead vapor. Yes, thank you. I wouldn't want to be around lead vapor. I'd be worried about that. Dewey Cheatham melts 4.51 kilograms of lead. What heat is needed?